Our goal is to calculate the solubility of copper 2 hydroxide, and we're given the solubility product constant, Ksp, which is equal to 2.2 times 10 to the negative 20 at 25 degrees Celsius. So let's conceptualize this problem first. Let's say we have some copper 2 hydroxide, which is blue. So let's say we put some copper 2 hydroxide, some solid copper 2 hydroxide into a beaker containing water. This is a slightly soluble ionic compound, so not everything we put into the beaker is going to dissolve. Let's say only a small portion of this dissolves. I'm going to take my eraser here. I'm going to take off a small bit of our solid there at the top, and let's say that small amount turns into ions. So what ions would we have in solution? Copper 2 tells us we have copper 2 plus ions in solution, so Cu2 plus, and then we also have hydroxide ions in solution, OH minus, so we'd have some hydroxide ions in solution too. Eventually we reach equilibrium, right? So we have a solubility equilibrium where the rate of dissolution is equal to the rate of precipitation. So let's go ahead and write that out. What's the chemical formula for copper 2 hydroxide? We could use this simple little trick here of crossing over your charges to figure out the chemical formula is Cu with parentheses, OH and a 2 here, right? So that's our solid. And we also have our ions, so Cu2 plus, or ions in solution. We also have hydroxide ions in solution, OH minus. We need to balance this, so we need a 2 in front of the hydroxide ions, and everything else here would get a 1. Alright, so let's set up an ice table. So we have our initial concentration, our change, and then finally our concentration at equilibrium. Well, before that small amount of copper 2 hydroxide dissolves, right, so that small amount that I erased earlier, we didn't have anything for the concentration of our ions in solution. So that's our initial concentration of our ions. It's 0. Now let's think about the small amount of copper 2 hydroxide, the solid that dissolved. Right, so let's say that X is equal to the concentration of copper 2 hydroxide that dissolves. Right, so we're going to lose a concentration of copper 2 hydroxide, which we'll say is X. Look at your mole ratios. For every 1 mole of copper 2 hydroxide that dissolves, we get 1 mole of copper 2 plus ions in solution. So if we're losing X for the concentration of copper 2 hydroxide, we're going to gain X for the concentration of copper 2 plus ions in solution. And for hydroxide ions, for every 1 mole of copper 2 hydroxide that dissolves, we get 2 moles of hydroxide ions. Right? So instead of X, it would be 2X. Right? So we're going to gain 2X for the concentration of hydroxide ions. So at equilibrium, right, our equilibrium concentrations of our ions would be X for copper 2 plus and 2X for hydroxide. All right, let's write our equilibrium expression, right? So Ksp is equal to, we look at our products, right? So we have Cu2 plus, so we put the concentration of Cu2 plus, and we raise the concentration to the power of the coefficient. And here our coefficient is a 1, so we raise this to the first power. Next, our other product here would be the hydroxide ions, so OH minus, and we raise that concentration to the power of the coefficient, which in this case is a 2, so we need to put a 2 here. And once again, we leave this pure solid out of our equilibrium expression. All right, let's plug in for Ksp, right? The solubility product constant was given to us. It's 2.2 times 10 to the negative 20. So let's plug that in. So this is equal to 2.2 times 10 to the negative 20. And this is equal to the concentration of copper 2 plus ions at equilibrium, which is X. So we put that in. This is X to the first power, times the concentration of hydroxide ions at equilibrium raised to the second power. So this would be 2x, and then we have to square it here. And this is where some students get a little bit confused because they say, well, you're doubling the concentration here, right, and then you're squaring it. Aren't you kind of like doing the same thing twice? But remember, these are two different things, right? This 2x is because of the mole ratios. Right? And we raise it to the power of the coefficient because that's what you do in an equilibrium expression. All right? So those are two different things. We're not doing the same thing twice. All right, when we do our algebra, right, on the right side, we would have x times 4x squared. So that's equal to 4x cubed, and this is equal to 2.2 times 10 to the negative 20. So we need to divide that by 4. All right, so we need to divide 2.2 times 10 to the negative 20 by 4. So you could do that in your head or on the calculator. 2.2 times 10 to the negative 20, right? We divide that by 4, and we get 5.5 times 10 to the negative 21st. So we have 5.5 times 10 to the negative 21st is equal to x cubed. All right, so to solve for x, we need to take the cube root of 5.5 times 10 to the negative 21st. And unfortunately, on this calculator, it's a little bit trickier than on most calculators. On most calculators, it's pretty straightforward and it's pretty easy to do. So let me show you one way to take the cube root of something on this TI-85 here. So we'd take the cube root, so we put a 3 in here, and then one way to find this is to go to second catalog, and then just move upwards here until you see the symbol. All right, so I don't see it yet, and there it is. So right there is the symbol we want. Right, so we're trying to take the cube root of, we want 5.5 times 10 to the negative 21st. And that should give us the cube root, which is equal to, let's go ahead and round that to 1.8 times 10 to the negative 7. So this is equal to, x is equal to 1.8 times 10 to the negative 7. And this would be the concentration, right? This would be molar. This would be the concentration of copper 2+ at equilibrium, right? Let's go back up here. So x is equal to the concentration of copper 2+ at equilibrium. And notice it's also equal to the molar solubility of copper 2 hydroxide, right? That's how much copper 2 hydroxide dissolved, x. So we found the molar solubility of copper 2 hydroxide. Our question asked us for solubility, so maybe they meant molar solubility, in which case we're done, or maybe they meant solubility in grams per liter. So let's go ahead and do that now. So this is equal to, all right, this is equal to the molar solubility. This is the molar solubility, which is moles over liters. What if they wanted grams over liters, right? You would need to have the molar mass of copper 2 hydroxide, right? So you could look that up on your periodic table. So copper 2 hydroxide has a molar mass of 97.57 grams per mole. So our answer here for molar solubility, this would be moles per liter. So if we want to go to solubility in grams per liter, let's look at our units and see what we'd have to do. We have 1.8 times 10 to the negative 7 moles over liters. Right? If we look at the molar mass, right, if we want to get to grams over liters, all we have to do is multiply the molar solubility by the molar mass, because the units for the molar mass are grams over moles. And if we multiply, the moles cancel, right? And we'll end up with grams over liters. So let's go ahead and do that calculation here. So we rounded this to 1.8 times 10 to the negative 7 was the molar solubility. To get to the solubility in grams per liter, we multiply that by 97.57, which is the molar mass of copper 2 hydroxide. And we get, if we round that to 1.8 times 10 to the negative 5. Right, so this is equal to 1.8 times 10 to the negative 5, and this would be grams over liters. So this is the solubility. Right, in 1 liter of solution, you could only dissolve 1.8 times 10 to the negative 5 grams. So copper 2 hydroxide is not very soluble at all. All right, so that's how to figure out the solubility if you're given the solubility product constant, KSP.